So we're going to look at the second example of a boundary value problem. So it's the same ODE as the last problem, just different boundary conditions. Remember, we're using y of x instead of x of x for this one. So start with case 1. Let's start with less than 0. Remember, lambda is going to be negative mu squared for that case. That would lead us to having... I know just from doing it, but I should write this out so you guys don't get confused. Solve the characteristic. Right? Little x plus c2 e to the little x, mu little x. General solution completed. Okay, y of prime of 0 is mu c1 plus, sorry, this should be minus mu c2, because e to the 0 is 1, equals 0. From this, we can see that c1 equals c2, right? So then y can be rewritten. Shouldn't one of these be minus? No. We're good. Right, so now we look at, sorry, I was looking at my notes and I confused myself because I did a different way in my notes than I'm doing right now. But we should be good. Y of pi, because I started with the other boundary condition for some reason. Doesn't matter. Y of pi is c2e to the mu pi plus c2e to the negative mu pi. So now we can take out a c2. Shouldn't that be minus? Oh boy. Oh yeah, so basically we can see here that no matter what, that it's just like the last problem. This right here cannot be equal to 0. It's always non-zero. Since it's an always non-zero value, that means that this just combines to make a new constant. We can call it whatever, say it's just new c2, so that's just c2 equals 0. Okay, so because of that, y is equal to 0, right? So c2 is 0. What was I just doing? Okay, so yeah, so then if c2 is 0, y is 0. So that's trivial. We don't want that, right? We want to find a non-trivial solution when y does not equal 0, because y is our eigenfunction. We don't want a 0 eigenfunction. Let's look at, I'll put it right here. Plenty of space. When y equals 0, y double prime equals 0, r is equal to plus minus 0, repeated roots, right? So then, what's the first one? Y prime of 0. That would be c2 equals 0. That will leave us with this. That would leave us, well, the second one, right? Yeah. c1 equals 0. If c1 0, y is trivial. No good. Okay, we have one left. Lambda greater than 0? Yeah. So lambda would have to be mu squared for that to happen. leaving us with and as you can see, that would be complex, right? So it's 0 plus minus mu I cosine mu x plus c2 sine. Like I said, I'm going pretty fast here, so go back to my other example, most definitely my overview video, if you want a more comprehensive breakdown. But this is all, oh, this isn't PDE's right here. This is ODE's, right? Oh, sorry. Y prime of 0 is mu c1 sine mu, well, that's 0. That goes to 0, right? I'm just going to not write that one down. This second term would still be there because it's cosine of 0, which is 1. So c2 is equal to 0. So then y is c1 cosine mu x. This has to be the runner-up for the eigenfunction, right? Hopefully. It's got to be. Y of pi. Yeah, it definitely is. Equals 0. So now we just have to figure out what value of mu pi would make that 0. And we've done this before in the overview, actually, where this would have to be... well, no, we just did in the last video, right? This is the same thing. It has to be any n minus 1/2 pi, right? Because cosine... For n, 1, 2, 3, right? Cosine of 1 minus 1/2 pi is cosine of pi over 2, which is 0. Cosine of 2 minus 1/2, 3 halves times pi. Cosine 3 halves pi is 0. So that works. Cross these out, solve for mu. Fantastic, right? I'm going to denote that as n because we have multiple mu's. It's a series solution. Then we can write our eigenvalue. Our eigenvalue is simply just mu squared, so right? Then our eigenfunction. Remember, we had only lambdas positive, right? Eigenfunction. If y sub n is equal to c sub n, because remember c can be anything. There's multiple y's. You have multiple constants based on which n you're using. Cosine n minus 1/2 times x. That is a terrible looking mu, by the way. Yeah. Okay, so that's that. This is for n1, 2, 3. Here is the answer. Look, I did it under 10 minutes. That's a new record right there. Remember, if I went too fast, this is just so you can see a different case. Go back to my overview video and check that one out. And I'm going to do 4 more examples. There's a few different cases. I'm going to do those ones fast as well. And then we'll move on to the next part. Because we're going to see a lot of this. When we do heat equation, wave equation, plus, it's going to be all of this in every problem. So I'll see you then. Hope you enjoyed the video.